Hello everyone, this is Vijetha, Associate Professor in the Department of ECE from MLR Institute of Technology. In this video, I would like to talk on RC phase shift oscillators from linear and digital integrated circuits. What are the topics which I want to cover here are: what is an oscillator, what are the conditions for oscillator, what are RC oscillators, and how to determine the frequency of oscillation for RC phase shift oscillator. An oscillator is basically a feedback amplifier in which a fraction of output is fed back to the input with the use of feedback circuit. See, an input is given to an amplifier. The output of amplifier is again given as a feedback to the amplifier. So, this is the block diagram of an oscillator. The two basic requirements for sustained oscillations are the magnitude of loop gain into the feedback gain must be equals to unity, and the total phase shift of loop must be equals to 0 or 360 degrees, that is angle between feedback gain and open loop gain should be equals to either 0 degrees or 360 degrees. RC oscillators. Inductors, capacitors required for the timing circuits which would be very bulky, whereas RC oscillators found to be more suitable, and there are two important RC oscillators which are RC phase shift oscillators and Wien bridge oscillators. Now, we will discuss about RC phase shift oscillators and how to determine the frequency of an RC phase shift oscillator. In the next video, we will cover Wien bridge oscillator. RC phase shift oscillator consisting of an op-amp as an inverting stage and cascaded with the RC network as a feedback circuit. The op-amp used in an inverting configuration, and it produces an output of 180 degrees phase shift at the output. As we are giving input to the negative terminal of an op-amp, we can say this op-amp is used in a inverting configuration. As it is used in inverting configuration, the output producing here will be 180 degrees out of phase. The cascaded RC network connects in a feedback network path, providing an additional phase shift of 180 degrees. Therefore, the total phase shift will be equals to 360 degrees, or we can say it as 0 degrees. When gain of amplifier is sufficiently large, the phase shift of the cascade RC network will be exactly 180 degrees. The circuit will oscillate the frequency determined by the RC feedback network. Now, let us consider the RC feedback network which is connected from the output of an op-amp to the input of an op-amp, where op-amp acts as an amplifier here. Let us consider V0 of S as the input for your RC phase shift RC network. At this node, the voltage is V1 of S. If you can apply a KCL across this node, you can add the current entering to the node is I1 of S. The current exit from this node will be I3 of S and I2 of S. So, if you can apply a KCL across the node V1 of S, we can write I1 of S is equals to I2 of S plus I3 of S, where I1 of S can be given as V0 of S minus V1 of S divided by 1 by SC, and I2 of S can be given as V1 of S divided by R, and here I3 of S can be given as V1 of S minus V2 of S divided by 1 by SC. So, I2 of S has been given with V0 of S minus V1 of S divided by 1 by SC, and I2 of S is given as V1 of S divided by R, and I3 of S is given as V1 of S minus V2 of S divided by 1 by SC. if you can solve this equation, like we can write this equation as SC into, we can rearrange this equation as SC into V naught of S minus V1 of S is equals to V1 of S divided by R plus SC into V1 of S minus V2 of S. We can also write it as RSC into V naught of S minus RSC into V1 of S is equals to V1 of S plus RSC into V1 of S minus V2 of S. So if you can rearrange this equation in terms of V1 of S, you can write, you try to take all the V1 of S equation to a LHS side, and you can write it as minus RSC V1 of S minus V1 of S minus RSC into V1 of S is equals to, you can take this V naught of S to a RHS side, and you can write it as minus RSC into V naught of S minus RSC into V2 of S. So if you can take minus common, you can write as V1 of S into 1 plus 2 RSC, which is equals to, if you can take common RSC over here, you can write it as V naught of S plus V2 of S. Here also I have taken the minus common from RHS side, and I also taken the minus from the RHS side, and I have rewritten the equation in such a way like V1 of S will be equals to V naught of S plus V2 of S into RSE divided by 1 plus 2 RSC. So this is how we determine V1 of S in terms of V naught of S plus V naught of S and V2 of S by applying a KCL across the node V1 of S. Now let us determine what happens when you apply the KCL across the V2 of S. So now here I am applying a KCL across the V2 of S, so that you can write the equation. The current entering here is I3 of S, and the current leaving from this node will be I5 of S and I4 of S. So I am writing this equation as I3 of S is equals to I4 of S plus I5 of S, where I3 of S can be given as V1 of S minus V2 of S divided by 1 by AC, and I4 of S can be given as V2 of S divided by R, which is written as V2 of S divided by R, and I5 of S given as V2 of S minus V of S divided by 1 by SC. Now if you can solve this expression, you can rewrite this as SC into V1 of S minus V2 of S is equals to V2 of S divided by R plus SC into V2 of S minus Vf of S. And you can also write like RSC is equals to V1 of S minus V2 of S is equals to V2 of S plus RSC into V2 of S minus Vf of S. So if you can rearrange this equation in terms of V1 of S, you try to get all the Vs of V1 of S towards the LHS side and remaining all to RHS side. You can rearrange this equation as RSC into V1 of S, which is equals to V2 of S. If you can take common, you can write as 1 plus 2 RSC minus this RSC into Vf of S. So you can write this expression as V1 of S is equals to V2 of S into 1 plus 2 RSC divided by RSC minus this Vf of S. So we can write this expression as V1 of S is equals to 2 RCS plus 1 into V2 of S divided by RSC minus Vf of S. Now here if we consider this R1 is much greater than the R, you can apply a voltage divide rule across here, and you can write Vf of S is equals to opposite voltage V2 of S into series resistance R plus the total, by applying a voltage divide rule across this node, Vf of S can be given as opposite voltage V2 of S into R divided by R plus 1 by SC. So, you can write this as V2 of S is equals to, this rearranging this as V2 of S is equals to R plus 1 by SC into Vf of S divided by R. So, you can write it as RSC plus 1 into Vf of S divided by RCS or RSC. So, you got three equations, two as V1 of S in terms of V1 of S, another one we got in terms of V2 of S. Now, this equation consisting of V2 of S. Now, you substitute this V2 of S in the V1 of S here, and also the V1 of S which we have determined across this node V1 of S. Here we have determined determined two equations across the node V1 of S and across the node V2 of S in terms of V1 of S, where we got the equation in terms of V2 of S. Now, at node Vf of S, you got the V2 of S. Substitute this V2 of S expression in these two equations. So, you can rearrange this expression as, see, V1 of S, in terms of V1 of S, we got V1 of S is equals to V0 of S plus V2 of S into RSC divided by 1 plus 2 RSC. Substitute this V2 of S in this expression, and you can write this expression as RSC into V0 of S divided by 2 RSC plus RSC plus 1 into Vf of S divided by RSC plus 1 will be equals to the voltage which we have determined here, 2 RSC plus 1 by V2 of S divided by RCS. So, substitute that equation here, that is 2 RSC plus 1. Another equation V1 of S is equals to 2 RSC plus 1 into V2 of S divided by RSC minus Vf of S. This equation we have determined across the node V1 of S, and this expression we have determined across the node V2 of S, and this expression we have determined across the node Vf of S. So, substitute this V2 of S over here and also over here, and this V1 of S will be equals to this V1 of S, and which you can rewrite this as RSC V0 of S divided by 2 RC plus 1 plus RCS plus 1 into Vf of S determined by 2 RSC plus 1, which is equals to 2 RC plus 1 into this RCS plus 1 into Vf of S divided by RCS square minus Vf of S. If you can solve this expression in terms of Vf of S and V0 of S, that is feedback by output. So, this is a feedback gain is given as R cube C cube S cube divided by R cube C cube S cube plus 6 R square C square S square plus 5 R S C plus 1. And the gain of an op amp, we know it as output by input, where the input voltage here is a feedback voltage. So, the gain of an op amp is given as V0 of S by Vf of S, which is given as feedback resistance to the input resistance, where in this circuit we used Rf as a feedback resistance and R1 as the input resistance. The gain, as the feedback is given to a negative terminal of an op amp, the gain of a inverting amplifier is given as minus Rf by R1. But according to the conditions of an oscillator, we can write A beta is equals to 1. A is a open loop gain, beta is a feedback gain. Feedback gain we have determined by using a RC network, and this open loop gain is given as minus RF by R1 as your input has been connected to a inverting terminal of an op amp. So now A beta should be equals to 1 is a condition for oscillation. So now minus RF by R1 into the beta value which we have determined by using RC network is R cube C cube S cube divided by R cube C cube S cube plus 6 R square C square S square plus 5 RCS plus 1 is equals to 1, which you can write it as minus R1 minus RF by R1 into R cube C cube. So you can rewrite this as minus RF by R1 into R cube C cube S cube will be equals to R cube C cube S cube plus 6 R square C square S square plus 5 RCS plus 1. By substituting S is equals to J omega, this equation can be given as minus RF by R1 into R cube C cube, J as minus J square, J cube can be given as, J cube omega cube, where the J cube is given as minus J omega cube is equals to R cube C cube and J omega whole cube. J cube is given as minus J omega cube minus 6 R square C square, J square is 1 and omega square, J square is minus 1, substitute the minus 1 over here. So minus 6 omega square R square C square plus 5 RC S is equals to J omega. So you can write as J 5 omega RC plus 1. Now from this expression, if you compare only the real parts, the real part across the left hand side is 0. So 0 is equals to minus 6 omega square R square C square plus 1. You can rearrange this expression as 1 is equals to 6 omega naught square R square C square, where you can write omega naught square as 1 by 6 R square C square. We know that omega is equals to 2 pi f. So omega naught square is given as 4 pi square f square is equals to 1 by 6 R square C square. So you can write f square is equals to 1 by 4 pi square 6 R square C square, and f is given as 1 by 2 pi root 6 RC. So you can write this f as 1 by root 6 2 pi RC. This is the frequency of oscillation. Now we'll compare only the imaginary parts. If you compare the imaginary parts, you will be getting as minus RF by R1 into minus J omega cube R cube C cube is equals to minus J omega cube R cube C cube plus J 5 omega RC. Here, by equating the imaginary parts, you can rewrite this expression as minus RF by R1 into minus J omega naught cube R cube C cube is equals to minus J omega cube R cube C cube plus 5 J omega naught RC. Now, if you can compare this, if you can take this as minus RF by R1 into minus J omega naught cube R cube C cube, here I am taking common as minus omega naught cube R cube C cube. I will take J also common, J omega naught cube R cube C cube. We can write 1 plus 5 by omega naught square R square C square. So here this minus J omega naught cube R cube C cube and here this minus J omega naught cube R cube C cube can be cancelled out, and this expression is given as minus RF by R1, which is equals to 1 minus, here if you have taken minus common, you will be getting it as a 1 minus 5 by omega naught square R square C square. You got this expression. So we got minus RF by R1 is equals to 1 minus 5 by omega naught square R square C square. So we got this f value, that is omega naught square value, as 1 by 6 R square C square. So if you can substitute this omega naught square as 1 by 6 r square, omega naught square, we got omega naught square is equals to and this equation can be minimized as minus Rf by R1 which is equals to 1 minus phi by omega naught square R square C square. But when we are comparing the real parts, we got omega naught square as 1 by 6 R square C square. If you substitute this omega naught square value in this expression, you can write it as minus Rf by R1 is equals to 1 minus 5 divided by 1 by 6 R square C square into R square C square, which you can write magnitude of R1 by Rf can be given as magnitude of 1 minus 5 by 1 by 6 which is 30 and which is given as magnitude of Rf by R1 is given as 29. So, Rf is equals to 29 times of R1. Therefore, the gain of an amplifier should be at least 29 and the total phase shift it will be exactly 360 degrees. So, here we have discussed about oscillator, that is the oscillator consisting of the oscillator is designed by taking a feedback to an amplifier, by connecting a feedback of an output of an amplifier to the input of an amplifier. And the conditions of an oscillators are magnitude of A beta should be 1 and angle between A beta should be either equals to 0 degrees or 360 degrees, where A is the gain of an operational amplifier, beta is the gain of a feedback network. And what are the different types of RC oscillators, where we are having two types, RC phase shift oscillator and Wien bridge oscillator. Here we have discussed the frequency response of an RC phase shift oscillator, or we can say the oscillation frequency. We got that f is equals to 1 by 2 pi root 6 RC, and we also determine the feedback resistance should be equals to 29 times of R1, so that you will be getting a oscillation, perfect oscillation. Next, in the next session, we will deal about Wien bridge oscillator. Thank you.